Here we're going to look at a reaction called a Diels-Alder Cycloaddition. So as the name suggests, a cycloaddition is the formation of one product, and that one product is cyclic. And a Diels-Alder Cycloaddition involves a reaction between something called a diene and something called a dienophile, something that likes dienes. The dienes are conjugated and are set, that basically means that the two double bonds are separated by a single bond. The simplest diene is buta-1,3-diene. The simplest dienophile would be ethene. Just dienophile is just a species with a double bond, and we get a very, very elegant reaction where these pi electrons are all going to move around and form some new bonds. Let's number the diene and the dienophile. So we'll call this is why it's called buta-1,3-diene. Obviously we've got ethene here, I'm going to number them 5 and 6. What we get then is the pi electrons between carbons 1 and 2 are going to move, and they're going to form a new bond between carbons 1 and 6. So we get a new sigma bond there between carbons 1 and 6. The pi bond, the red pi bond between carbons 5 and 6 is going to move. That's going to form a new sigma bond, a new single bond between carbons 4 and 5. And the pi bond, the blue pi bond between carbons 3 and 4 are going to move and form a new pi bond between carbons 2 and 3, a new double bond. And the product is going to be a cyclohexene. And these Diels-Alder reactions are always going to produce some form of either cyclohexene or something with a cyclohexene ring. So what we get then is, I'm going to number this carbon 1. We can see that we form a new bond between carbons 1 and 6, and that was using the pi bond, which I've given the green colour to. So I'm going to give this the colour green to show that the pair of electrons in this pi bond is now used to form a sigma bond between carbons 1 and 6. The bond between carbon 6 and 5, nothing's changed there. It's this sigma bond here is the same as this sigma bond. This is carbon 4, so obviously this bond is new, and it's formed from the red pi bond, so we're going to give that the red colour. And then we've got carbons 3 and 2. So we can see that this black bond between carbon 3 and 4 is the same as this black bond. The black bond between carbons 2 and 3 is the same as that black bond, but we've got a new pi bond formed between carbon 2 and 3, and we give that blue colour. So that's probably the simplest, or that is the simplest Diels-Alder reaction. But we can make them a little bit more complicated. Let's now consider that my diene is now cyclohexa-1,3-diene, which is this compound. So that's my diene now, and I'm going to number this again. 1, 2, 3, 4, but this one now is 5 and 6. And my dienophile, I'm now going to make a little bit more complicated. I'm going to make it this unsaturated ketone, and I'm going to number this at 7, 8, 9 and 10. But the same principles will apply. The pair of electrons between carbon 1 and 2 are going to form a new bond, this time between carbons 1 and 8. The pair of electrons between carbons 7, 8 and 7 are going to form a new single sigma bond between carbons 7 and 4. And we're going to get a movement of a pair of electrons between carbon 3 and 4. And that's going to form a new pi bond between 2 and 3. So what's my product going to look like this time? Well, remember, it's going to have a cyclohexene ring in it. I'm just going to move this down a little bit. So it's basically going to have this structure. So I'm going to copy this and put that down. But I will need to change the numbers a little bit, I think. Change these numbers. So what we've got now is, this now is carbon 8. As you can see, the new bond between, this new bond formed from the pi bond between 1 and 2 now is between 1 and 8. This, therefore, is now going to be number 7. And we formed a new bond between carbon 7 and 4. Yes, we did. It's there. I'll just scribble this out. So this is carbon 8. And you can see on carbon 8, I've still got carbons 9 and 10. Nothing's changed there. So let's add that in. So we've got carbon 9 and carbon 10. But there is something missing. What has happened to carbons 5 and 6? Well, carbon 6 is bonded to carbon 1 and nothing's changed. It still is. So I need to put carbon 6 there. Bonded to carbon 6 is carbon 5. And carbon 5 is bonded to carbon 4. So we have to put that in. So that's carbon 6. That's carbon 5. And that gives us something called a bridged cyclic compound. We've got this bridge here over the ring between carbons 1 and 4. Now, an application of this reaction is the synthesis of a compound called buprenorphine, which is used to treat heroin addiction. And buprenorphine is synthesized from a natural product that's obtained from opium, which is called thebaine. So we've got thebaine here, which is very similar to the structure of morphine. I think morphine would have hydrogens here, and it wouldn't have these double bonds. So there is some subtle differences. Now, to get from thebaine to buprenorphine, you can see there's quite a lot of structural differences. So we've demethylated to form this phenol group, and we've got this sort of cyclopropyl group here, and we've got this group here. What we're interested in is getting this bridge. How do we get this bridge? And that is done by a Diels-Alder reaction. Now, if you've understood what we've done here, then we should be fine, because what we've got in effect is this cyclohex. This is in effect the same as this here, isn't it? It's cyclohexane-1,3-diene. So they are the same in effect. They've just got a lot of scaffolding here around it. And the dienophile that we use is exactly the same as what's used in this example. So you can see that if you react this diene with this dienophile, we will get this product. And again, product structure there, you should be able to figure out from this product structure here. I've literally just made carbon 2 and 3 the bridge, rather than carbons 6 and 5, but they're basically the same thing. So that's an example of a Diels-Alder reaction. It's where the Diels-Alder reaction is important. Obviously, as I've said, to get from this compound to buprenorphine, we need to do a few more reactions, which obviously involves reducing this double bond and changing some things here. Out of interest, this ketone would react, and you could add all this group on via a Grignard. So you just add a Grignard reagent with this as your R group. This would need to be demethylated to form the secondary amine, and then that amine would react with this basically with a chlorine on it, and that would give you this cyclopropyl group. But the interesting bit there, I thought, was the Diels-Alder. Diels-Alder reaction is very important, and that is where an example of where you can use one in synthesis.